Hello, and welcome to today's webinar. My name is Jamie Jimenez, and I am the Marketing Manager for TFF Systems here at Repligen. And during today's webinar, we'll be exploring innovations in mixing vessel technology for TFF through a case study we conducted at one of our manufacturing facilities. Now, as today's presenter, Luke Smith, walks you through the study, you'll find a lot of analysis went into the limitations and drawbacks of conventional mixing methods, as well as the technological innovations needed to provide a superior end product. And so really, in a sense, the thrust of today's webinar is all around innovation. And that's what really drives us here at Repligen. That's our mission. You see, we have an established track record of developing and launching new innovative technologies with in mind to create fully integrated solutions for upstream and downstream that will empower you to develop and manufacture with greater efficiency, accuracy, and yields. So, if you're new to Repligen, or your only experience with us up until this point has been around solely TFF systems, I just want you to know that we have a wide array of solutions and offerings, ranging from hollow fibers to flat sheet cassettes, chromatography systems with resins and pre-packed columns, cell culture perfusion via our XCell ATF, TFDF systems, and then a vast assortment of fluid management solutions to bring everything together. And so with that in mind, before we hand things over to Lucas, there are three things I want you to keep in mind for this webinar. Number one, the webinar is being recorded and will be made available for on-demand viewing at Repligen.com. Number two, we have a live Q&A panel that you can access on the right-hand side of your screen, where questions can be submitted at any time during the webinar. And finally, as those questions come across and you find yourself wanting certain questions to be prioritized and answered over others, keep in mind that there is a upvote feature where you can prioritize those questions and we can address them during the live Q&A. And so with all of that in mind, let's hand things over to Mr. Lucas Smith, Commercial Project Manager for TFF, so he can walk us through this case study.
Hello, everyone. My name is Luke Smith. Thank you for joining today. Today, we're going to talk about how good mixing can benefit your TFF production, as well as use membrane performance during die filtration to analyze the mixing performance of Repligen's CrossFlow RS TFF system compared to traditional vessels. In TFF, practice and common sense dictate that if I maintain the same operating and process conditions around my filter, then I should have consistent membrane performance, both between batches and during scale-up. But that's not always what happens. How many times have you experienced changes in membrane performance right after scale-up or between batches? And if I'm maintaining my molecular weight cutoff, my filter format and chemistry and TMP and CFF, why do I start seeing deviations arise? This is at the heart of what our study will address today. That of all the parameters that are often monitored and maintained during TFF, feed consistency just often isn't one of them. Now, for some processes, particularly at lab scale, the recirculation flow back into the vessel alone provides adequate mixing. However, more often than not, we just assume we have great mixing as we scale from stir bars to big process tanks. So we miss issues like inconsistent feed properties created by inadequate retentate vessels and the lack of homogeneity, and end up with poor membrane performance. And that's really the issue. The primary source of feed consistency issues is due to limitations and drawbacks of conventional mixing vessels. The reality is that most mixing vessels used in TFF applications today don't meet the intense mixing demands of TFF processes. Inadequacies in the mixing dynamics of most vessels can allow stratification, localization, or short-circuiting, as demonstrated in this animation. Here we can see that the addition is not completely mixed in the vessel, but allowed to go nearly untouched out to the filter, creating a portion of the feed with an abnormally high concentration, and likely leading to lower membrane performance. All of these types of conditions lead to just that, variations in the feed delivered to the membrane. This is why adopting a method for analyzing the homogeneity of the feed in early stage development and utilizing the right mixing vessel is so critical. By doing these two things, we can optimize the TFF process to reduce the headaches that come from deviations at larger scales. If we can maintain a homogeneous feed solution, then our process will be more efficient, more easily controlled and within tighter tolerances, and be more predictable. But how do I know that my feed is homogeneous? The good news is you don't need some fancy new tool or widget or enhanced computer modeling to analyze your feed consistency. The best tool is something you already have. You can monitor your membrane's performance during TFF process to watch for feed inconsistencies. Today we are going to focus on one TFF process, and that's diafiltration. During diafiltration, we are using the filter membrane to separate a solute, such as salts or proteins, from a solvent, while simultaneously diluting with a new solvent. This is often used in bioprocessing to exchange one buffer for another while retaining your target proteins. Typically, this process is tracked by the number of vessel volumes transferred through the membrane before we completely change from one buffer to the next. Here's a graph showing the theoretical exchange rate curve as a function of diafiltration volumes during constant volume diafiltration, meaning we are bringing an equal amount of new buffer to the volume being removed. So we maintain a constant volume within the retentate vessel. On the x-axis, we see we have the number of diafiltration volumes, and on the y-axis, the percent of the buffer which has been exchanged, meaning once we reach a 100%, then we have completely changed from one buffer to the next. What we see here is the theoretical curve makes sense. As the rate of exchange or slope of the curve at the beginning is high, while the concentration of the buffer being removed is high. Then, as the concentration decreases, we see its rate of removal decrease until we reach 100%. As we track this process, if our retentate vessel is providing the membrane with a consistent, homogeneous feed, we should see our performance match this theoretical curve. Now, understanding what we should see, let's do a performance analysis. As part of this case study, a control run was executed, using a traditional feed vessel in which the new buffer was delivered directly below the liquid level, as shown in this little diagram. Mixing was produced by a single impeller and by the recirculation flow of the retentate as it returned to the vessel, both positioned towards the bottom of the tank. We can see plotted here a comparison of the buffer exchange profile of this control run in light blue, with the theoretical we just discussed in red. Prior to the first DV, the control profile shows a lower degree of exchange than expected by the theoretical, meaning that the feed to the membrane during this stage has a higher concentration of the retentate than would be expected from a homogeneous solution. Beyond the first DV, the control profile exceeds the theoretical, suggesting a higher buffer concentration. But we know that in an ideal homogeneous condition, we shouldn't see this. So we can see that inconsistencies in the feed solution to the membrane affect the permeate flow across the membrane. You might look at this and say, well, they both reach 100% buffer exchange at about the same time. What's the big deal? Well, one, you're right. In this example, the number of diavolumes was the same. However, what this chart doesn't show is the amount of time that it took. Decreased flow rates extend how much time your product spends circulating around the retentate feed loop. More time equals more exposure to shear, meaning poor product quality. Second, while we didn't see it here, the areas of high concentration, as we saw in the control prior to 1 dB, can cause permanent fouling of the membrane and restrict flow throughout the remainder of the process. But in this analysis, all we're looking for is the deviations from the theoretical, so that we can identify whether or not our feed is consistent. And that's exactly what we saw. Comparing the two, it can also be difficult to see the significance of the difference. For example, if we look at about 0.2 dV, in the control, we've only seen about 4.5% buffer exchange, while theoretically, we should have seen already over 22%. So let's look a little closer as to why we are seeing these deviations by getting a close-up to what is happening at the filter. The performance of the membrane is highly dependent on the tightness and thickness of the layer of retained molecules pressed against the membrane surface. This is often referred to as the gel layer. The formation of this layer has a direct effect on both the permeate flow rate and selectivity of the membrane. Even small changes in cross-flow flux, transmembrane pressure, or feed characteristics have an immediate effect on the formation of this gel layer, and consequently, on the permeate flow rate. So, by observing the buffer exchange profile during diafiltration, we are monitoring these conditions around the membrane. Because the membrane is so sensitive to the feed, we can use it to directly and accurately monitor those feed variations, which are truly significant to performance. Let's go one step further in understanding the results of this control test. If we plot the diafiltration agreement ratio, or how closely the actual performance followed the theoretical, on the y-axis, as a function of diafiltration volumes, on the x-axis, we can gain more understanding of the differences in the two profiles. Now, under ideal retentate vessel conditions, the percent agreement should be at 100%. In the areas below 100%, the addition buffer concentration is below what is expected. In areas above 100%, the addition buffer concentration is higher than expected. Overall, we can see that the deviation of the actual versus the theoretical in this control run is quite significant. Next, we'll move to analyzing the mixing performance of Repligen's mixing vessel. But first, I want to introduce you to its unique design and features. Our tulip tank, to my knowledge, is the first single-use mixing tank specifically designed for optimizing TFF performance that's available on the market today. It is a square self-baffling tank with a uniquely designed sump section. The tank has two independently controlled impellers, which allows for mixing in both the sump and the upper volume. It also has multiple return lines. This helps distribute the retentate throughout the tank, enhancing mixing. As the fluid level drops, like during concentration steps, the system uses the load cells to detect fluid level and slow or stop the impeller before they reach the fluid surface to prevent high shear churning and foam creation. It also uses the system's valves to adapt the route of the retentate flow to prevent air introduction and foaming from returning above the surface level. You'll also notice that unlike conventional vessels, like we saw in the control run, the addition is not brought directly into the tank. Instead, the addition enters into the retentate return flow, so it begins to mix into solution before entering the tank and is more evenly distributed. The sump features baffled walls and a flow diverter, which routes the flow along the walls rather than directly to the center above the outlet. The sump also has an anti-vortexing outlet design, which allows you to run at higher CFF rates, even at minimum working volumes. With conventional vessels, on the other hand, which use a dish-shaped bottom, towards the end of concentration or while doing low diafiltration volumes, the CFF must be reduced to prevent sucking air into the pump, which causes damage to the product. This also decreases how low they can operate overall, usually only being able to operate, even at low CFF rates, down to around 5 liters. The tulip tank, on the other hand, can have a range from 150 liters all the way down to under 3 liters without needing to slow the CFF. With the multiple return lines, dual mixers, the square self-baffling design, baffled sump, and flow diverter, you can see how this vessel was designed to provide optimal mixing conditions. The goal of this study was to test if it actually does. For the study, 2 TFF runs were conducted at distinct process conditions and monitored during buffer exchange diafiltration. These runs were performed on the Repligen Crossflow RS30 TFF system with a 50-liter tulip tank. You can see the process conditions for these runs in the table here. Because the volume of the 40-liter run, run A, is well above the upper impeller, both the upper and lower mixers were utilized, with each set to 100 RPM. As well, both retentate return lines were used. These conditions were chosen to evaluate the mixer's performance with a high volume and relatively low CFF rates and impeller speeds. Those of you with a keen eye for mixer design may have noticed with this tank that if you were to be running at a volume where the upper impeller and upper return lines shut off, then you may be left with a section of the fluid above the sump which may not be mixed by the lower impeller and lower return flow in the sump. If you did, good work. You're a smart cookie. The 10-liter run B, was specifically designed to test just that. If there are zones created which are not mixed, then we would expect to see deviations in the buffer exchange performance profile as those sections reach the membrane. The results of these two tests were analyzed using the same method we did for the control. Here we see the percent agreement profiles for runs A and B, the lines in red and dark blue, plotted alongside the results from the control run. Looking at the profiles for runs A and B, we see that there was a high peak right at the beginning and a low peak just before 1 dB. But they are very short in duration, and despite the peaks, the exchange rates were within plus or minus 10% of those expected under ideal conditions throughout the entire diafiltration. This indicates that the vessel was able to quickly reach homogeneity and maintain it. It's also interesting to see that despite the significant difference in the process conditions between the two runs, the result profiles are nearly identical, meaning that the system was able to provide equally great mixing in both circumstances. It also shows that those potential dead zones in run B we discussed earlier mixed just fine, because we didn't see significant deviations in performance. In stark contrast, we see in the control run significant deviation from theoretical, and it doesn't settle within that plus or minus 10% we achieved in the two-loop tank until after 2 dB, meaning it took over 2 dB for the conventional vessel to reach and maintain homogeneity. Overall, we see that these two runs, that the vessel was able to provide the membrane nearly ideal conditions. Similar conditions apply to the whole Crossflow RS family. Each was designed with the same principles in mind to optimize TFF performance and help maintain consistency and scale up across all scales. The family features mixing bottles from 1 liters, 5 liters, and 10 liters to the two tank vessels seen here in the study, available in 50 liters and 150 liters. Each of these systems are designed to minimize short circuiting, ensure efficient mixing, and help you maximize your yields. So, just to summarize, we've developed a method of analyzing feed homogeneity by tracking diafiltration exchange performance. Using this method, we've been able to analyze the performance of conventional mixing vessels and noted the deficiencies in their performance. We then reviewed the design features of our Crossflow RS30 TFF system and analyzed its performance in providing a homogeneous feed, and saw that it was on par with the theoretical model of ideal mixing. Our study revealed that the RS30 showed drastic improvements over traditional mixing vessels used in TFF applications. The key takeaway here is that our Crossflow RS TFF system and our two-loop tank can be used in TFF applications to provide more reliable or optimized performance that's easier to control and scale. I want to thank you for joining us today. If you're interested in seeing these systems in person or getting additional product information, please feel free to contact myself or your local account manager. You can also find data sheets and product family brochures and links for requesting more info on our website. And with that, I'll turn it over to our marketing team to run a Q&A session.
All right. Well, Lucas, thank you for taking the time to walk us through that fascinating case study. And so now we're going to transition to the live Q&A portion of our webinar. And today, instead of just having Lucas do all the work, we actually have a panel of folks joining us. So Lucas Smith, Commercial Marketing Manager. And we also have Dave Bianchi joining us. He is the Director of Global Downstream Field Applications here at Repligen. Dave, I know that's your title, but I think most people just call you the master of TFF here. And then we also have Steve Cates, who is the Chief Technology Officer here at Repligen. And this panel of folks is going to be helping us address all of the questions that you have been sending in. And so to kick things off, Lucas, I know we just put you to work, but real quick, we've got a question here. How is the buffer exchange calculated and monitored?
Yeah, that's a great question. So for this study with diafiltration using salt solutions, we used conductivity sensors to monitor the progress of the buffer exchange by measuring that the concentrations of those salts through the buffer exchange. Dave, Steve, anything you want to add to that?
Yeah, no, that's perfect. Inline buffer conductivity monitoring. If you have particular excipients in buffer B compared to buffer A, you can monitor that as well. But it's all about inline and sampling.
Yep.
Perfect.
And I would echo Dave's comments. Yeah, I agreed.
All right. Excellent. So with that in mind, Steve, this question is for you. How do you recommend how to analyze run-to-run consistency?
Well, essentially what you're going to do is you're going to take samples and either offline samples and measure conductivity or measure concentration of the product using something like Flow VPE, where you can take it offline, or you can actually install a Flow VPX, which will actually monitor the concentration directly online as you're recirculating through the system. So you can get very accurate feedback values, and you can actually use that as transition set points from initial concentration to diafiltration to final concentration. So it's a very effective way to do that.
Excellent. All right. And so here is a question coming in from Jeremy. So can data from this type of system be reliably extrapolated to larger scales and different systems? Lucas?
I can hop in. Oh, okay.
Go ahead, Dave.
Yeah.
Sure. Hi, Jeremy. Scalability is always a good question. And while we love to say TFF processes are totally scalable, as tanks get larger and larger, mixing efficiency certainly becomes more difficult. So yes, it can. The concepts can absolutely be extracted. The analysis that we developed for this study could absolutely be utilized at a larger scale. I think that answers the question.
Mm-hmm. Excellent. And so, let's see here. So, do you expect to improve flux, time, reproducibility, scaling, or recovery when you run a process with sample? So, a question along those lines.
Yeah, that's a big question to unpack, actually. So yes, I mean, mixing efficacy is really important to all of those concepts. Process flux, for instance, if you have a situation where you are in a poorly mixed tank and you're seeing stratification or short circuiting in that sort of situation, that's going to cause the flux to crash out. So by effectively mixing your tank and avoiding those scenarios, yes, you will see an improvement in flux, and obviously an improvement in flux also means a reduction in process time. Reproducibility, I think Steve's question, the question that Steve answered earlier, kind of captures that. Inline monitoring, absolutely. For those of you who have studied statistical processing, SPC, analyzing recorded data and data trends over time, that's really, really important. And scaling the Jeremy question that I just answered before, it's kind of this is the same idea there.
Mm-hmm.
Anybody else have anything else to add?
No, that's good, Dave. I think our SPC is definitely important for this.
Yeah. All right, excellent. So then, how does the system account for, things like void, holdup volumes that may be in the lines or tubing? Lucas, why don't we have you jump in here? Because you were walking us through the RS-50 in that animation, and there were multiple inlets going into the tank, right?
Yeah, that's a great question. So when we design these systems, we actually put a lot of work into avoiding any type of void and minimizing all the holdup on the system. One of the unique technologies that we use that allows us to do that is using injection molded manifolds, silicone manifolds, instead of hose barb manifolds or tubing sets. And the advantage of this is we can get our pinch points or valves really close to the main flow path so that we avoid practically eliminate dead legs, and we minimize the holdup volume of the entire system by not having all of those hose barb connections. It also makes the flow path really reliable. But for example, if we look at all those return lines that you brought up, Jamie, it could be if we couldn't install our pinch points really close to where those branch off, then we would have a considerable dead leg there, and as well as increase the holdup volume. But because of where we can locate our pinch points, because of those injection molded manifolds, we eliminate those dead legs.
Got it. Excellent. So just sticking with the concept then of the design of the vessel, there's a question here. I think you mentioned self-baffling in your presentation. So what is a self-baffling tank? What does that mean?
That is a great question. So if we look at the development of mixing vessels and vessels in general over time, we started back with a circular or round tanks, right? And to be able to keep the flow from just circling around the outside of the tank, we installed baffles or bars on the walls of the tank that would divert the flow back towards the center of the tank, allowing it to mix rather than just spinning around the outside of the tank. With a square tank, it's self-baffling, meaning we don't have to install those bars or fins on the outside, but just by nature of being square, the product will be forced back to the center of the tank where it continued to mix with the bulk of the solution.
Got it. Excellent. Very helpful. All right. So I know we're coming down to the wire here. One question, and I'll open this up to the whole group here. So did you consider use of a conical shaped bottom instead of a tulip shape? In multi-product facilities, the optimal size of the tulip bottom may be different product to product. Interested in your thoughts on the pros and cons.
I'll jump on this first. Bruce, this is a really, really good question. We actually tested before we developed the tulip tank. We tested conical bottom tanks as well, just trying to make it a little bit less complex. But the problem for us was minimum recirculation volume and trying to improve that geometry there. Traditional two-stage tanks have always been much more suited for concentrating to a higher level, so you can go like a 30x concentration or 50x concentration versus a conical bottom, because there's only so much you can set up in the conical bottom and recover safely before you start foaming and denaturing your protein or product. So the tulip was definitely the best approach for that, and it allows us. We have one size tulip that fits on a 50 liter, 100 liter, and a 150 liter, and the volume in the tulip itself is about 2.3 liters. So it's definitely the best approach to the conical bottom. And anyone else want to jump in on that as well?
Yeah, I can hop in a little. Actually, I mean, the neat thing about the presentation that Lucas gave is we developed a method to characterize the mixing efficacy of any tank. So yeah, by all means, it'll be useful for if you are using a conical bottom tank or a different size tulip sump. You could absolutely do the same study for yourself and apply it to that same theoretical model.
Mm-hmm. Excellent. All right. Well, I know that there's several other questions in the queue, but we are actually out of time. So, gentlemen, I want to thank you for taking the time to be with us today to field these questions. Lucas, thank you again for the case study. It was excellent. And just so that everyone's aware, for those of you, if we haven't had a chance to address your questions, we will be following up. And for everyone who's tuned in today, we will be following up with an email. So if you have any questions as it relates to this case study, as it relates to the RS family of products, or anything that Repligen could help support you with, please don't hesitate to reach out, and we'll see you next time. Thanks again, everyone.
Thanks.